All right, let's begin section 8.4 by talking about magnetism. So here, imagine that this is going to be a bar magnet, and all magnets have to have two poles, and we call them a north pole and a south pole. Just think of them as names. And magnets have to come in those pairs. Each one has to have a north and a south, because if we break them apart, we just break them into two smaller magnets. And each one of those magnets would have a north pole and a south pole. And even if we do that all the way down to the atomic level, we find that like a single iron nucleus would still end up having a north pole and a south pole. It has to do with the way the electrons are moving. It gets complicated. But as far as we know, you can't just have a north pole by itself. Even though you could have like just a proton by itself, a positive charge, you can't have a single pole by itself. They have to come in pairs. And just like with charges, we would say that like poles would repel. So a north pole put next to a different north pole, the two magnets would push each other apart. If you put a north pole next to a south pole, so opposite poles, they would attract. Opposites attract. So here we have a big bar magnet, and we're going to say that that's fixed. It can't move. It can't spin. And here we have a tiny little magnet that can spin, and we can call that a compass. So the compass will spin to align itself with the magnetic field from this larger magnet. So can you see that this white part of the magnet right here, that's going to represent the south pole, has been attracted to the north pole. So it has spun as close as it can to get to the north pole. And if I move it over here, the compass will spin until the red side, which represents the north, is going to be attracted to the south pole of that magnet that it's now closer to. So the opposites attract. The north of the compass is attracted to the south of this other magnet. And you could also think of that this pole right here, this south pole of the compass magnet, is repelled, which is why it's as far away from the south pole of this bar magnet that it can get. So if we wanted to kind of map out the effect of the bar magnet around it, we could do that with a magnetic field. Just think of it as an imaginary map around the bar magnet of what a compass would do if we put a compass there. So can you see that in this animation, the magnetic field is going to be little imaginary compasses all over showing how they would align. So here, near the North Pole, the compass's white south pole would point towards it. It would be attracted. But over here by the bar magnet's south pole, the compass's little red north pole would be attracted and point towards it. So then we could imagine putting a compass there, and it would show us how it would align. The field is a map of the bar magnet's effect. So if you want the north pole of a compass, the red pole of a compass, to point in a certain direction, you notice that it's going to point towards the south pole of a magnet. So what does that mean for the Earth? Right. So if I were to have a compass right here near the surface of Earth, the little red compass magnet points to the north, and that's the way we've defined north. The little red part of the compass that points north, we call that the north pole of the magnet. But it's attracted to south poles. So the Earth, if we think of it as a giant magnet inside, because it does have a global magnetic field, it does have a gigantic magnetic field, its magnetic south is at the North Pole. So Earth's magnet has the South Pole at the North Pole. But that is why a compass's North Pole points that way. So if I move the compass here to the equator, can you kind of see how the compass is parallel to the ground? If we imagined a person standing right here, the compass would point directly north or directly south, kind of parallel to the ground. But here at the pole, the magnet would try to just align vertically, pointing into the ground and up into space. And here at the latitude of Minnesota, somewhere here, The magnet does kind of point north, but if it were free to spin, it would also try to point down into the Earth a bit. And you could kind of figure out your latitude on the Earth, how close you are to the North Pole or the equator, by figuring out how much the compass would try to dip towards the ground, and that's called your dip angle. But usually in Minnesota, when I'm holding a compass, I hold it flat in my hand, and I only let it spin kind of horizontally. I don't allow the compass to dip vertically. On paper, the way we illustrate the magnetic field, the imaginary map, is a little bit different. So if we had a north pole of a bar magnet and a south pole of a bar magnet, we would indicate the magnetic field lines kind of coming from the north and wrapping around to the south. I've only sketched 5 field lines in here, but you could draw more. But what they would indicate is the way a little Sampis compass would point. And so can you see that the field line was going from the North Pole towards the south? It was like flowing this way. That indicates which way your North Pole of your compass would point. And the south would point backwards along that field line. So if I was to put a little compass right here that was free to spin, it would point along that field line. And remember, the field line flows from north to south. And the south pole of that magnet would point that way. And just like with the electric field maps that we had drawn before, it's strongest where these field lines are kind of crunched together. So here I'd say that the field lines are kind of spread apart. So I would say that it would be weaker out here. But here is where it is stronger. And one thing that weirds me out is that a lot of books don't show this. A lot of like simple explanations on the internet don't show this, and it confused me until I actually learned why. But the magnetic field is strong throughout the whole magnet as well, because these magnetic field lines actually make whole loops, which is different than the electric field lines. So this whole region is a very strong magnetic field because the field lines are very crunched together in there. The abbreviation for magnetic field, if you ever happen to see it, is a capital B. And in physics classes, we tend to also draw a little kind of hash arrow over the top of it. But feel free to just write out magnetic field. You don't have to know the B for this class. So there are certain types of materials called ferromagnetic materials. Think iron for one of them. And let's say originally that this chunk of iron, this ferromagnetic material, is not magnetized. But it is made up of material that could be magnetized. So what we could do is expose it to a strong magnetic field. So let's move this bar magnet that's already a magnet close to it. And there's that strong magnetic field. See how all the field lines are scrunched together? And that strong magnetic field can force kind of the atoms in that material to turn or twist and to realign themselves to match the bar magnet's field. And then once you take that magnet away, they're mostly stuck like that. So now overall, these little magnetic fields in this material are all aligned now. Think of these little arrows like little compasses. They're all aligned. So now overall it is a magnet. Like before, see how they were all pointing different directions? That tended to, each little magnetic field canceled out. But if you can coerce them, they will align. And then it can stay a magnet. Now it can lose its magnetism over time in different ways, like if it gets hit with something, or maybe it's exposed to a different magnetic field, or maybe it just gets hot. All of those things can cause that magnet to lose its magnetic field. But what if you don't have a strong bar magnet already and you want to make a magnet by kind of coercing the electrons in iron to all line up? Well, you can use electricity to make a magnet, and that is an electromagnet. Now the book covers the magnetic field line around a single straight wire and a single loop of wire, but we really don't use those in everyday life. What we use in everyday life are coils because it magnifies the effect. So let's take a battery. Right now it's set to 10 volts and it's just hooked up to a loop of wire. So you can imagine it's pumping current through the wire, so you can see the little electrons flowing through there. Since all of the electrons are kind of flowing the same way in each loop, their magnetic effect of these electrons flowing in the loop add up. So if we add more loops, we would make the overall magnetic field stronger. Each loop adds on more magnetic field. Oh, it looks like 4 is the most I can go, so let's decrease it. Can you see the compass drawings, the magnetic field getting dimmer, and now it's going to get stronger as I add loops? So if you wanted a strong electromagnet, well, you could get a higher voltage battery that would push more current through, that would make more magnetic field. Or you could just add more loops. Now if I change the direction of the voltage so that the current flows in the opposite direction, watch what happens to the magnets. So right now pick a magnet part of this magnetic field and just watch it. So I'm watching this one and I see the white is pointing towards the coil. But if I flip the voltage and make the electrons flow in the other direction, the magnetic field also flipped direction. Here I can just show you quick too. If I turn down the voltage, the magnetic field should get dimmer or weaker. So one thing I would do, like at science fair tables, I would make all the kids that come to my table make an electromagnet. I'm like, really all you need is a nail and some wire and a battery. And the nail inside there, we would pick something that would be ferromagnetic, something with some iron in it, and that magnifies the effect. Also, extra loops around that nail would magnify the effect. Also, getting a more powerful battery would as well, but you want to keep it, you only want it to be a few volts, that way it's safer for the kids. Okay. And then the only safety thing I would really warn them about is that this wire can get hot because there's so much current flowing through the wire. It's not going to choose to flow through your hand because your dry hand has a huge resistance. It'll choose to flow through the wire, but all that current will heat up the wire. So if it gets hot, you just drop it. But once you have it hooked up and it's touching the top of the battery and the bottom of the battery, so it's making a full circuit, the current is flowing, it will generate an electric field, and you should be able to pick up some nails or paper clips, even if those things weren't magnets, because a magnetic field can induce a temporary magnet in other objects. What else should I write on here just to make sure you have some notes? Like poles repel. So that would be north by north or south by south. Opposite poles attract. A magnetic field maps out the effect around a magnet. Right. Magnets have two poles. A magnet can align, which you could also say is magnetize, certain other materials. And current moving in loops makes a magnetic field. And maybe I didn't point this out earlier, but you notice how this bar magnet has kind of a field that comes from the north and wraps around to the south? The electromagnet has the same type of shape. So it's almost like there should be a bar magnet inside here, but inside that coil of wire is empty, but it makes the same shape. And that magnetic field goes through the coil of wire and wraps around. So then we could say, much like a bar magnet. And we could also say Earth's south magnetic pole is at the north, which draws our compasses North Pole toward it.